Hey guys, Mr. Mitchell here, how's it going? In this video we're going to go over 6 worked examples to show you how to do problems involving electric field strength. Now if you haven't already done so, check out my previous video covering the theory on this topic, and that way you can apply what you learned in that video to this one. So let's get into it. Question 1 says that an electron with a charge of minus 1.6 times 10 to the minus 19 coulombs is in a field of 4,000 newtons per coulomb. Calculate the force on the electron. Well, writing down what we know from the question, we're trying to find the force F. We know the charge is minus 1.6 times 10 to the minus 19 coulombs, and the electric field strength E is 4,000 newtons per coulomb. So writing down our equation relating F, Q and E, we get F equals QE, and substituting in the numbers gives us minus 1.6 times 10 to the minus 19 times 4,000. Putting that into your calculator should give you an answer of minus 6.4 times 10 to the minus 16 newtons. Question 2 says that the dome of a Van de Graaff holds a charge of 0.4 times 10 to the minus 5 coulombs. Calculate the electric field strength at a distance of 1.5 meters from the dome centre. Well, this time we're dealing with a charged conducting sphere here. So writing down what we know from the question, we're trying to find the electric field strength E. We know that the charge Q is 0.4 times 10 to the minus 5 coulombs. We know that epsilon naught is 8.85 times 10 to the minus 12 farads per meter from the datasheet. And lastly, the distance R from the centre of the dome is 1.5 meters. So writing down the equation for the electric field strength at a distance from a charged conducting sphere, we have E equals Q over 4 pi epsilon naught R squared. Substituting in the numbers gives us 0.4 times 10 to the minus 5 divided by 4 pi times 8.85 times 10 to the minus 12 times 1.5 squared. Putting all this into your calculator should give you a final answer of 1.6 times 10 to the 4 newtons per coulomb. Question 3 says that a point charge X of plus 3 microcoulombs is placed a distance of 0.1 meters from a point charge Y of minus 5 microcoulombs. Calculate the electric field strength at a point P, 0.3 meters from the 3 microcoulomb charge as shown below. Well, what we need to do here is find the electric field strength at point P due to both charges X and charge Y separately, and then add them together as a vector sum. Firstly, let's find the electric field strength E at P due to X. So writing down what we know from the question, we're trying to find EX. We know that QX is 3.0 times 10 to the minus 6 coulombs. We know that epsilon naught is 8.85 times 10 to the minus 12 farads per meter. We know that Rx is 0.3 meters. That's the distance there from X to P. And writing down our equation, we have Ex equals Qx over 4 pi epsilon naught Rx squared, where we're just using x's to keep us right here. And substituting in the numbers, we have 3 times 10 to the minus 6 divided by 4 pi times 8.85 times 10 to the minus 12 times 0.3 squared. And putting all of that into your calculator should give you a final answer of 3.0 times 10 to the 5 newtons per coulomb. Doing the same now but finding the electric field at P due to Y, we're trying to find EY. We know that QY is minus 5 times 10 to the minus 6 coulombs. Epsilon naught is 8.85 times 10 to the minus 12 farads per meter. Ry is 0.2 meters, and writing down our equation, we have EY equals QY over 4 pi epsilon naught Ry squared. Putting in the numbers again, we have minus 5 times 10 to the minus 6 divided by 4 pi times 8.85 times 10 to the minus 12 times 0.2 squared. Putting all of this into your calculator now should give you an answer of minus 1.12 times 10 to the 6 newtons per coulomb. Now we've got our two vectors, but we need to add them in a vector sum, so we can write that the total electric field strength equals Ex plus Ey, which is equal to 3 times 10 to the 5 plus minus 1.12 times 10 to the 6, which we've just calculated, and putting that into your calculator should give you a final answer of minus 8.2 times 10 to the 5 newtons per coulomb. And the direction of that vector will be to the right. Question 4 says that 2 point charges QA and QB are placed at points A and B where the distance AB equals 0.5 meters. Calculate the total electric field strength at the midpoint of AB. So there's our charge A and there's our charge B, and we want to find the electric field strength midway between the two charges. And firstly, you can see labelled on the diagram here is that since the two charges have the same sign, the electric fields at the midpoint of AB will be in opposite directions. In other words, the charges are repelling each other as shown by these directions. However, since charge B is greater in magnitude, then EB to the left will be larger, so the total electric field strength will be to the left. Let's now find the electric field strength at the midpoint due to charge A and charge B separately. So the electric field strength at the midpoint due to A, writing down what we know, we're trying to find EA. We know that QA is 2 times 10 to the minus 9 coulombs, epsilon naught is 8.85 times 10 to the minus 12 farads per meter, Ra is 0.25 meters. So writing down our equation, we have EA equals QA over 4 pi epsilon naught Ra squared. Substituting in the numbers gives us 2 times 10 to the minus 9 divided by 4 pi times 8.85 times 10 to the minus 12 times 0.25 squared. And putting all of that into your calculator should give you an answer of 287.7 newtons per coulomb. Doing the same now but for charge B, finding E at the midpoint due to B, we're trying to find EB. We know that QB is 3 times 10 to the minus 9 coulombs. We know that epsilon naught is 8.85 times 10 to the minus 12 farads per metre, and RB is 0.25 metres. Writing down our equation, we have EB equals QB over 4 pi epsilon naught RB squared. Substituting in the numbers gives us 3 times 10 to the minus 9 divided by 4 pi times 8.85 times 10 to the minus 12 times 0.25 squared, where we're using half the total distance between the two charges, which gets us to the midpoint of 0.25 metres. And putting all of that into your calculator gives an answer of 431.6 newtons per coulomb. So remember, electric fields need to be added as a vector sum, and in this case they're all lying on the same line, on the same plane. So since the electric fields are going in opposite directions, we could write that E is equal to EA minus EB, which gives us 287.7 minus 431.6, and if you put that into your calculator you get a final answer of minus 144 newtons per coulomb. And we already said at the beginning the direction of this is going to be to the left. Question 5 says to sketch a graph to show how the electric field strength varies with distance for a charged sphere. Well, our sketch should look something like this, where we've got the electric field strength E on the y-axis and the distance R on the x-axis, and this is our radius point here. And we can note that inside the sphere, our electric field strength inside is 0, whereas outside the sphere, their electric field strength varies with 1 over r squared, which is an inverse square law. Lastly, question 6 says that a metallic sphere has a radius of 0.04 metres. The charge on the sphere is plus 30 microcoulombs. Calculate the electric field strength A inside the sphere and B at the surface of the sphere. Well, inside the sphere, remember the electric field strength E is equal to 0 newtons per coulomb. And at the surface of the sphere, where the electric field strength will be a maximum, we're trying to find E. We know that Q is plus 30 microcoulombs, which is the same as 30 times 10 to the minus 6 coulombs. We know that epsilon naught is 8.85 times 10 to the minus 12 farads per metre, and the distance r is 0.04 metres at the radius. So writing down our equation, we have E equals Q over 4 pi epsilon naught r squared. Substituting in the numbers gives us 30 times 10 to the minus 6 divided by 4 pi times 8.85 times 10 to the minus 12 times 0.04 squared. Putting that into your calculator should give you an answer of 1.7 times 10 to the 8 newtons per coulomb. And the direction of this will be away from the sphere. And lastly, part C says to calculate the electric field strength at a distance of 1.0 metres from the centre of the sphere. Writing down what we know from the question, we're trying to find the electric field strength E. We know that Q is 30 times 10 to the minus 6 coulombs. Epsilon naught is 8.85 times 10 to the minus 12 farads per metre. And lastly, the distance R this time is 1.0 metres. So writing down our equation, we have E equals Q over 4 pi epsilon naught r squared. Substituting in the numbers gives us 30 times 10 to the minus 6 divided by 4 pi times 8.85 times 10 to the minus 12 times 1.0 squared. Putting all of this into your calculator should give you a final answer of 2.7 times 10 to the 5 newtons per coulomb. And again, the direction is away from the sphere. That's all for this video, folks. Thanks for watching. If you made it to the end, I really appreciate it. Make sure to give the video a like, subscribe to the channel, and I'll see you in the next one. Take care.